Let's take a look at our next lesson in our unit on inductive and deductive reasoning. We're going to be looking at section 1.4, where we're going to focus on proving conjectures and specifically looking at deductive reasoning. So what we want to accomplish in this lesson is to help you understand how we go about proving mathematical statements using logical arguments. What are some of the strategies and methods that we use to make sure that we make our point conclusively? There are some vocabulary terms that you should record and be looking for. Make sure you understand by the end of the video what a proof is, what we mean by generalizations, what is deductive reasoning, transitive property, and a two-column proof. So be looking for those words and make sure that they are clear once you're finished listening. So to start off with, I want to start by just giving you a definition for a mathematical proof so you will understand what it is we're trying to accomplish. So a proof is a mathematical argument showing that a statement is valid in all cases, or that, in other words, no counterexample exists at all. So we're going to be taking a look at how do we create something that actually proves beyond a shadow of a doubt, completely airtight, that something is true, so that we know for certain that there's no counterexample out there that could come in and knock our idea out of the water. In order to understand that, we will use, when we begin our proofs, we'll start with generalizations. We'll start with ideas or assumptions that everybody knows to be true. So we start there. And then once we have the generalization, then we use logical reasoning, usually algebra, to pull out a conclusion from that. And that process, going from a general assumption through the algebra or the logical reasoning up to a final conclusion, is what we call deductive reasoning. And hopefully the difference between inductive and deductive is now becoming clear to you. Inductive, we take things that we see around us, make observations about it, make some sort of conjecture, but we have not proven it to be true. We find examples that support what we say. We can even find counterexamples that show us when something is invalid, but we do not prove things. That is what is left to deductive reasoning, to follow a certain prescribed style and theory to be able to show that something is true beyond a shadow of a doubt. So we're going to start, and we're going to use deductive reasoning to prove that the product of an odd integer and an even integer is even. So what we have to do to start with is find a way of describing an odd integer or an even integer that we can all live with and accept. And so you'll see in the text of this one that I started by saying 2x was my even integer. Keep in mind that x could be any number under the sun. It might be even, it might be odd, it doesn't matter, because if I put a 2 with it, it will definitely become an even integer. 2 times anything is the definition of what it means to be even. And then my other number, which I'm going to call y, since I don't know where it starts, I don't know if I'm starting with y being an even or an odd number. To make sure, I'm going to turn it first into an even number. And then I know once it's even, if I add 1 to it, it will definitely be odd. So I use these two numbers as my generalization. These are the guys that I know I can count on. This guy is even, 2x, and this guy is odd. So now I'm going to take those two and multiply them together. So now kicks in my algebraic instincts. I know that if I have two things multiplied, I'm going to use the distributive property. So I'll get 4xy plus 2x. Now here comes the part where I'm kind of being strategic. I need to show that my answer is an even number. So if I pull a 2 out away from this, and that leaves me with 2xy plus x, this could be any number at all. I have no idea, a combination of an even number and an odd number and adding them and multiplying. Who knows? It's some number in here that we can all admit. It's a some number. As long as I multiply it by 2, I now know that my answer is even. So the final conclusion is where we kind of pull it all together and we say, since this thing right here is an even number, then the product of an even integer and an odd integer is even. And really, if you look closely, all I've done is quoted the question basically right there. Let's try it again. Let's use deductive reasoning to prove that the difference between consecutive perfect squares is always an odd number. So one thing you want to look at as you're looking at this and writing it down is that these are meant to be consecutive numbers, and we're going to take their squares and find the difference. So I need to set it up so I start with consecutive numbers. So there you have it. I start with x, and the next number beside x would be x plus 1. So these are my two numbers. And what I'm going to do is find the difference of their perfect squares. So now I'm going to be a little strategic here to begin with because I need to find the difference between these numbers. And I know if I put the biggest number first and subtract the smaller, that at least I'll avoid any extra negatives. So I'm going to do that. I know this one is bigger. So I'm going to put x plus 1 in squared first minus x squared. And so I'm just going to use my algebra. This squared is x squared plus 2x plus 1 minus x squared. The x squareds cancel, and all I have is 2x plus 1. Now, I already talked about it in the last question. 2x plus 1 is an odd number. So here I go. Since 2x plus 1 is an odd number, then the difference of consecutive perfect squares is odd. And what we've done here is we've started with a generalization. We've done some logic in here with our algebra, and then we've come to a conclusion that is a complete proof. There is no possible counterexample that could come in and blow this theory out of the water. And keep in mind that what we're doing when we go through this process is we are using deductive reasoning. Okay, so now just a reminder as we go through. If you remember from the title page that I used when I was doing 1.4, you'll notice that I put this picture. And some of you may recognize this as Aristotle. And so the question is, why would I put Aristotle on the title page for deductive reasoning? Well, Aristotle is best known as the founder of formal logic. The philosopher's goal was to come up with a universal process of reasoning that would help people be able to learn anything. He's known for so many things. Aristotle clearly was a genius. He dabbled in mathematics and medicine and art and all kinds of character qualities. Very brilliant man. And so what we know is that he was the one that first dabbled in the idea of, okay, what are the rules of the game, so to speak? How do we prove that something is true? And so that's why I have put him on the title page of this, because he is the beginning of formal logic. If you Google Aristotle, you're going to find a few quotes that are really very interesting. I picked a couple just so you get a taste for this man's mind. The first one, the high-minded man must care more for the truth than for what people think. That is a very profound statement, and you will see that as you live out your life. People who are ruled by doing what people think around them, what they're worried about, what others will say, what others will think, hardly ever are the ones that go to that higher calling of doing what is true or what is right. So a high-minded man has to care more for the truth than for what people think. This one is one that teachers often quote. Those who know, do, but those who understand, teach. To be able to truly teach, you need to understand. You can't just do math. If you're a good mathematician, you do math. It doesn't mean that you actually understand and can teach it. So it's kind of one of our mantras. And then anybody can become angry. That's easy. But to be angry with the right person, to the right degree, at the right time, and for the right purpose, and in the right way, that is not within everybody's power, and it is not easy. Just those quotes give you a sense of the depth and the character of this philosopher that we look to, Aristotle. Now we're going to move on just a little bit here and look at some of those standard sort of procedures around logic, and one of them is called the transitive property. This is actually a very simple property to understand. So as we look at it, let's take a look. And what I want you to focus on is down here. This is the easiest part. And what it says is, if A is equal to B, and then B is equal to C, then we know that A is equal to C. Math works like that. We know when quantities are equal to the same thing that they're equal to each other. And this is the transitive property that we're using, a very famous form of logic. Now, if we used it in this question, weightlifting builds muscle. Muscle makes you strong. Strength improves balance. The question would be, okay, if Ines lifts weights, what can be deduced about Ines? Well, if Ines lifts weights, then he he or she is improving their balance. You could also say they're building muscle and they're getting strong. We can also come to this final conclusion: if Ines lifts weights, then he's improving his balance. That's just a simple, clear example of the transitive property as we work through it. Here's just a goofy one. Penguins are black and white. Some old TV shows are black and white. Therefore, some penguins are old TV shows. Down the bottom, logic, another thing that penguins aren't very good at. Clearly, what those things have been placed together make no sense in their connection to one another. But the transitive property, we love to kind of poke fun at it for sure. So we'll check some more of those out a little later as we go through. Now, before we try the next question, I also just need to introduce to you two-column proofs. Two-column proofs are basically exactly what they say. We create two columns, and in the left column, we write the statements. Right? We write down the things that we see are happening. And on the right-hand side, we write the justification for what we're seeing. And hopefully that leads us to some kind of conclusion that we were meant to conclude. So use a two-column proof to prove that when two straight lines intersect, the vertically opposite angles are equal. Okay, so what we're going to look at is basically two lines that intersect each other, and we want to be able to prove that 1 and 3 or 2 and 4 are equal to one another. Okay, so I'm going to use a little bit of the transitive property here eventually, but let's see what I'm doing. I'm going to focus first on angle 1 and 2. And what I know is angle 1 plus angle 2 adds up to 180 degrees. I know that because of the definition of a straight line, or you could say supplementary angles. Now, I'm just going to move that around a little bit. I'm going to move 2 over to the other side. So angle 1 is equal to 180 degrees minus 2, angle 2. And that's just the subtraction property of equations. Nothing very fancy there. Now I'm going to leave that alone for a minute. And now I'm going to go and talk about angles 2 and 3. And what I know is that if I take 2 and 3 and I add them together, they also add up to 180 degrees because of the definition of a straight line. So now, strategically, I know what I'm trying to get to here, and that's where I'm going. But I know that angle 3, if I move my angle 2 over to the other side, is equal to 180 degrees minus 2. All I've done is subtract the angle from the other side. Now, before I finish with this one, I'm actually going to just make a switch. So I'm going to take this that's on the right and put it on the left, and this one to the right. So what I have is 180 degrees minus angle 2 is equal to angle 3. Now, I've highlighted them. I'm going to take this guy. If this is equal to that, and that is equal to this, then I know that angle 1 equals angle 3. And that is using the transitive property. And what I've shown is that these angles across from one another are congruent. Okay, so just a warning and a reminder. Remember that demonstrating using an example is not a proof, right? So we have to have a way of backing up and using a general case to be able to actually prove something that is true. And here's just a chart that helps us remember the differences between these things. Induction, looking around at the patterns around us, seeing patterns and making note of them because of the examples we see. Sherlock Holmes being a really good example of that. But remember, these are not proven. Whereas deduction is where we are taking an idea, something that we all know to be true, we're working logic on it, and we're coming up with proving something, a confirmation of what we have. And Aristotle is our sort of figurehead for that one. Okay, so there you have it. That's just the tip of the iceberg, but a good place to start for proving mathematical statements using logical arguments. Here's your homework. Make sure you give each one of these questions a sincere try so that you can grapple with the things that make sense and the things that you still need help with. Make sure you bring those questions to class. Good luck, everybody.